let's get some practice in identifying functions. So, if given a set A that contains the elements 1, 2, 3, 4 in blue, and given another set B containing the elements 2, 4, 6, 8 in black, is the function from A to B defined by this set of ordered pairs a function? Well, in order to answer this question, we of course need to know the definition of a function. So a function from A to B must be a subset of the Cartesian product of A and B, or A cross B, where every element in A has to have exactly one element in B so that the ordered pair is an element of our function. So what do we have to check in this definition? Well, first thing you should check is that obviously this is in fact a subset of the Cartesian product of these two sets. The second thing we should check is that every element in A is going to be mapped onto something in our codomain B. And finally, we need to make sure that when we are mapping something to our codomain B, that each element A only maps to something once. So these are the three categories we need to check to verify something is in fact going to be a function. So what do we see here? First, to check if it's a subset of the Cartesian product. And the answer is going to be yes. How do I know this? Well, first of all, A cross B means that the ordered pairs we have to be such that what's on the left-hand side is an element of A, and what's on the right-hand side is an element of B. That's what that means. So let's check every single one here. I've already highlighted it in blue, so it's more obvious. As we can see, everything on the left-hand side of these ordered pairs does in fact appear to be an element in our A. We have 1, 2, 3, and 4. And everything on the right-hand side does in fact appear to be an element of B. There's nothing here that's like, for example, 1, 7, right? This would not be part of a subset of a Cartesian product because 7 is not an element of B. So yes, this does in fact seem to fit our first criteria. Okay. Our second criteria, we need to check that every single element in A maps onto an element in B. So is that true? And how do we see this? Well, you just have to make sure that in our function here, everything here has to appear here. So is there a 1 in this function? And the answer is yes, there's a 1 right there. Is there a 2 in this function? And the answer is yes, there's a 2 right there. Similarly for 3, the 3 appears here, and the 4 appears here. There is no element in A that does not appear in our function. So it does in fact seem to meet our second criteria. The last criteria we need to check is that every time we take an element from A and map it to B, to an element in B, it has to only map to that element in B once. It cannot map to something in B twice. So we cannot have something where 1 maps to 2 different elements in B. So let's quickly check that. Another way of asking this is, does 1 appear once? Does 2 appear once? Does 3 appear once in our function? So let's go ahead and check that. Well, 1 only appears once, 2 only appears once, 3 only appears once, and 4 only appears once. So it looks like it meets all 3 criteria. If you're still struggling to understand why this is in fact true, let's draw out these sets. So we've drawn out our 2 sets A and B, and now let's draw the function, or draw the arrows. So what do we have? 1 maps to 2. So what we do is we take the 1 here, and we draw an arrow to 2. Okay, that's this part of the function complete. Now let's look at 2. 2 maps to 4. So we take our 2 and we map it to the 4 in our codomain. Next, we take the 3, we map it to a 6. And then we take our 4 and map it to an 8, like so. Okay, so what do we see here? Well, first we see that, of course, this is in fact a subset of the Cartesian product because none of these arrows have to leave, right, any of the sets. Like if we had like 7 here, right, if we mapped 4 to 7, it wouldn't be a Cartesian product because 7 is not in B. So we know that it's definitely a subset of the Cartesian product. Fantastic. Next, every single thing in our domain, our A, has to have an arrow pointing to something in our B. So that's what this really means. Everything in A, every element here, has to have an arrow pointing away from it. We cannot have something like a blank or an element that hasn't been mapped. And that does in fact appear to be true. Everything here has an arrow pointing away from it. And the last thing to check is that exactly one arrow is pointing away from every single element in A onto our codomain B. And that is true. There's only one arrow pointing from A, one from 2, one from 3, one from 4, one from 1, sorry, not one from A. So that is how you can better see that it meets all 3 of these criteria. So it is in fact true that this is a function.